Okay, next we'll spend some videos on the calculations of derivatives. And I will first give you a standard list of derivatives. Now, all this material can be found in sections 2.2, 2.3, 2.5 and 3.3. A whole bunch of scattered results. So, okay, we start with the standard derivatives. And there's a small list of these which you have to know by heart. What is the first? Well, suppose that we look at the function x to the power r and we compute the derivative. What happens? Well, we get r in front and we decrease the power by 1. Okay, so this is this thing. R, the power, cannot be equal to 0. Well, we already saw a small example because we computed the derivative of x squared and we know that it is 2x. Now, do we get the same result if we apply this rule straightforwardly? Yes, because 2 comes in front, the power goes down by 1, and 2 minus 1 is equal to 1, and x to the power 1 is equal to x. Obviously, if we add a constant, nothing changes, because if we compute the derivative of a constant, so this is denoted by the c, then we get 0. I mean, if you increase the height of a mountain by a fixed amount, then of course the slope doesn't change. That is expressed by this constant. Now we get the derivatives of the 3 trigonometric functions, so computing the derivative of sine of x gives you the cosine. The derivative of cosine of x gives you minus sine of x. You can just look at it in the picture. I will do in a minute. Give you a small sort of hint, at least to remember about the signs. If you compute the derivative of tangent of x, we get 1 over cosine squared. Okay, so can we at least remember a little bit how the relation between the derivatives of sine and cosine? Well, if you look at the picture, then cosine goes like this. Sine is going up first and it goes like this, so it's a little bit shifted, and you see that if at this part, so this is sine of x. Now cosine is decreasing, is negative, so the derivative, the slope, is negative, and in this area the sine is positive, so we must have that the derivative of the cosine is minus the sine. Now if you look at the sine of x, it's positive. I mean the slope is positive, and cosine is positive on this part as well, so the sines are equal. It's just a sort of hand waving thing. I mean, it's no proof, obviously. Okay, now we get e to the power x. This is the unique function which is equal to its own derivative. That's why it's very important. That's why e is such an important number. If you compute the derivative of the natural logarithm of x, we get 1 over x. And the same happens, but a little bit in an extended form, that if we compute the derivative of x in logarithm of the natural logarithm of x in absolute value, then we also get 1 over x, but now the natural logarithm of the absolute value is defined for all x, and the natural logarithm of x is defined only for positive values of x. Now what is the absolute value of a number? It's equal to the number if this number is non-negative, positive, so it's greater or equal to 0, and it is equal to minus the number if this number is negative. So what it does is in fact delete the minus sign in front of a number. I can say something more, that if you compute the derivative of a to the power x, we know that that the logarithm of x with base a is just a constant multiple of the natural logarithm of x, and its vector is the natural logarithm of a. And we have a similar thing with the derivative of a to the power x. It's just the natural logarithm of a multiplied by a to the power x itself. And now you see again that the natural, if you plug in e here, then we get, what do we get then? Then we get that the derivative of e to the power x is the natural logarithm of e multiplied by e to the power x, and the natural logarithm of e is 1. So these things, at least at first sight, are not inconsistent. I'll give you one or two small examples where people tend to make mistakes, and it's just more of, say, a habit of knowing how to work with all these powers. So we want to compute the derivative of the function which is equal to 1 over square root of x. Now we don't have derivatives of square root of x, at least given, at least at first sight. So we have to rewrite it a little, and we know that square root of x is equal to x to the power 1/2, and the power in the denominator becomes minus the power in the numerator. So we get the derivative of x to the power minus 1/2, and now we can apply the rule over here with r equal to minus half. So minus 1/2 comes in front, and the power decreases by 1. And then we again just try to figure out what this power becomes. So minus half minus 1 is equal to x minus 3 halves. And then this we don't like, well, you can leave it like this, but you can also rewrite it a little bit by putting again this negative power into the denominator by deleting the negative sign. So we get minus 1 over 2 multiplied by x to the power 3 over 2. You can make it a little bit more elegant by recalling that x to the power 3/2 is equal to x to the power 1 times x to the power 1/2, and so we get x squared times square root of x, replacing x to the power 3/2. Now clearly, if we have compute the derivative of x to the power 0, well, what is x to the power 0 is 1 by definition. The derivative of 1 is a constant, so the derivative is equal to 0. Okay, this rule of course does not apply in that case. That's why we have this condition that the power should not be equal to 0. One final example, so if we have to compute the derivative of the nth root of x, then again we have to change the nth root into a power, so this is equal to x to the power 1 over n. Computing the derivative, we use this rule with r equal to 1 over n, so 1 over n comes in front, and the power decreases by 1. And now we rewrite it a little bit again. X to the power 1 over n minus 1, we put this into one fraction, so we get 1 over n minus 1 is equal to n over n, just to make the denominators equal. So we get a 1 minus n divided by n, and it is slightly more elegant to write it as x to the power minus n minus 1 over n. And just a matter of a minus sign. I think this would be the best option. Of course, this is correct as well.